the intention today is to do this thing. Three purposes that I would want to highlight it, that this is for revision only, and there is no bouts of that I make about details. Second thing, it's for self explanation only. That is, I'm trying to practice here for myself and not for you, which means if there are errors, you can avoid them, because at no point did I mean that there were not supposed to be any, or it was supposed to be an all correct, all invasive, whatever session. So it's meant to be for me, so I learn from my mistakes and this becomes more interactive for me personally. So I will do everything that's basically correlation. Then next is, yes, wait, after correlation I think I linear regression. Then I will do other things like that, which are multicollinearity, multicollinearity. Then heterosidacity. Then there's one more topic that we all know exists, that would be my autocorrelation. So these are the topics that I would want to cover. So yes, so that's how we'll start. Now I'll start with my initial topic, which is correlation theory. Now, correlation theory, what would that mean? Correlation theory would mean degree of relationship between two or more variables. Now what would that mean? That means that if I have two variables or more variables like x, y, and another variable like that is of z, what relationship do they encompass? They can have, or any kind of relationship. They can have a relationship like this, or they can have a relationship like this, or they can have a relationship like so, any kind of relationship that they can have. Now this is again divided into further halves, which is two kinds of relationship, which is one is simple, another is multiple. Simple is between two variables, right? And this one is between two or more variables, right? So this is the agenda here. Now there are other kinds of relationship also, like positive correlation. That would mean if they have same direction in which they move, if x is increasing and y is increasing, and if x is decreasing then y is decreasing, that is, they are directly proportional to each other. Then the other kind of relationship is negative correlation. Now that would mean their direction of change is opposite. So one is moving upwards, the other is moving downwards. Or if one is one is decreasing, then the other is increasing. That means they are inversely proportional, right? And there is one more kind, no correlation. That would mean increase or decrease in x has no correlation whatsoever to any increase or decrease in y. Right? Now, one thing to note very important here is correlation is not causation, which means if x is increasing and y is increasing, that would not necessarily mean that x is increasing because y is increasing or vice versa. What his hair situation is, it just so happens that whenever x is increasing, y also seems to be increasing. That's it. Which is why if we say cigarette smoking has somehow any relationship with cancer and people are more prone to have more cancer due to cigarette smoking, it's just that they happen to be people who were cigarette smoking were also found to have cancer. There's no direct causation that anybody has suggested as of yet. There's no direct proof of that yet. It's just a causation, correlation that we will say is happening here. Now, this is the sign I depict my linear correlation with. Right? So how do I make this? If I write, I can write basically our relationship between x and y will be summation xi yi upon summation xi square summation yi square. Now if I do square of this thing, it will basically become something like summation xi yi whole square upon summation xi square summation yi square. I can also write this, if you know this we will discuss this again, so don't worry, but I'll just put it because we are doing it right now also once. This can also be written like this, right? Which would mean summation yx upon xy is equal to r square. So that would mean that here what I've written, this is xi minus x bar and yi minus y bar, right? Now another thing to note, which we would always know, is summation xi is always equal to 0 and summation yi must be equal to 0 for most, and summation xi yi is greater than 0. So now if this is greater than 0, then rxy will be positive. If so, these two are the results that we can basically derive things from. That is, you can see this, these are the two results that I can say from this point. So this determines my position here, that if this is positive, this will be positive, this is negative, this will be negative. That is, correlation between xy is positive here and correlation between xy is negative here. Now moving ahead, now this is done. I will put this in one more wording to save our time, this is what we wrote, right? Wait, this is what we basically, I can also write this as n as x as y. So here what is where sx would be summation xi square by n, and sy would be, this is standard deviation just in case anybody does not know. Again, this class is not meant for basic, it's meant for revision, so just in case anybody is after me, I'm sorry if it was not quite detailed, it was not meant to be. Now we will see another thing. So this is a very important proof in the Econometrics book of Kutsiani's, which I've always loved, like the proof I've loved. So if this is my y and this is my x and this goes my y bar and this goes my x bar, and this is my line AB, right? So this line forms an angle theta with my y bar line, okay? And so from here I can calculate deviation, that is yi minus y bar, and from here I can calculate my, see if this is my x, right? So this is my x bar, so I can calculate that like this, my xi. Now what are we going to do is, if there is perfect positive correlation, right, then you all know that tan theta is equal to perpendicular upon base, which would mean perpendicular here is y and base here is x. So this will be my, so this would mean y is equal to tan theta into x, right? So then what I'll do is, we all know the formula of r by now. That would mean I'll substitute this value of that I've calculated just now here. This is a direct proof in Kutsiani, just in case it's become a problem for any of you. I am assuring you this is direct proof from Kutsiani, so don't be bothered. That would mean summation x square upon summation x square tan theta so this will become 1. Yeah, so this is my correlation coefficient. So basically, if this is my, if this positive, I can basically assume that this theta will result into this thing. Yes. It can also, yeah, it is pretty, yeah. Now I'll go to rank correlation. Let me zoom in back. rank correlation. So rank correlation is if there are two variables x and y, what will I do is I'll rank them in similar manner, whatever ascending or descending order, I'll rank them, and then my R will be equal to this formula 1 minus 6 summation d square n into, right, this would be my formula. I think this is the right formula. If I'm not mistaken, I don't think I am. Very rare chance, but just in case, let me just confirm. Where is this? Is the one that I'm looking after? Oh, for wait. Wait. I think this is the formula. How did it? Wait. Yeah, this is the formula. So I'm right. Yeah, so this is the formula where my D is the difference between ranks of x and y, right, and n is number of observations. Now one thing that I think missed is R. R will usually lie between -1 and 1, whereas R square will lie between 0 and 1, and I think that's the only way. So if anybody asks you any otherwise, no, this is how it works. Now we'll go to partial correlation coefficient. Partial correlation relationship between any two variables, right, when all others are held constant. So this would be my partial correlation coefficient. So if I have two variables that I want to find a relationship with, and third one is constant, it will go like R12 dot 3 is equal to R12, the correlationship between R1 and 2, minus correlationship of 1 with 3 and correlationship of 2 with 3, right? Then what will I get in the below is 1 minus R13 square and 1 minus R23 square, right? Similarly, if I have to find a correlation between R13, 2, it will become R13 minus R12 minus R23. Now these other two are the one which I will take in denominator, which is minus R12 square minus R23 square, right? So this is relationship between x1 and x3, where x2 is held constant, right? So this is it. Now there are certain limitations of my R also. What are the limitations? Number one is R is only for linear relationship, wouldn't work for a multi-collinear relationship. So at any given point in time, here also is trying to find only relationship between 1 and 3. I'm never trying to find a relationship between more. Second limitation would be R is correlation, not causation. Okay, moving ahead. Now I will do very quick thing while we move to regression, which is a very stated doubt for most of the people that exist, right? So there is two variables x and y. Then how will I have four different kinds of lines is what we are going to do. If the true relationship between x and y is, assuming that y is the dependent variable and x is the independent variable, this will go like now. True relationship number 1, then we will have true regression line. True regression line would go something like expectation of phi I is equal to beta 1 plus beta 1 xi. Right, now third is my estimated relationship. This would go something like yi is equal to beta naught cap beta 1 cap xi plus ei. Fourth is my estimated regression line. This should be my so you get the gap right between everything. This is how we started and this is how it became. The yi cap is very important to understand what we are after, these caps upon betas, whether it's a standard, estimated, or which is a true regression line. We're mostly going to be in this business only. From this we will draw assumptions about the other business. If I had to wait yes, this I will draw. This we're doing, and we're going to make one more line which is going to be dotted. And similarly we'll have one more dotted line. Wait, so what I'm trying to do here with this is, again, yes, so this would be my right? So this is thing that I wanted to be out of this. I don't think I've been clear or crisp with here, but whatever. Could have been better. Who said? Quite a lot. Confusion has become. You can ignore this. I was not pretty ideal with this. If you want this, you can open Kutsiani's. Maybe I'm not saying that I know this. So moving ahead. Now this is CLRM. Wait, I think I figured it out. Wait. So this is my XI and this is my A, B, right? This is my Y cap and this is my UI cap, right? And this is my UI and this is my this. Oh, I figured it out. I did not. Never mind. So, CLRM. Now this will be my classical linear regression model. Okay, so this is my classical linear regression model. So here relationship between two variables is given by this. Now this is my error term. This is my independent or exogenous or explanatory variable, and this is my explained endogenous or target variable. I like to call them as independent and dependent, so that's the terminology we will go with. Moving ahead, now the relevance of UI is something that might come up in syllabus, which was like omission of random variables. So U becomes like important. If there are important variables missing in the model, U becomes a catch-all variable, so it definitely fills a lot of gap. Then it covers up for unpredictable element. And then it covers up for incorrect specification or misspecification. Then it covers for aggregation errors, because we are dealing with such large data at a time that aggregates can have still something missing or are subject to error, and measurement errors, like the variables that we are using to estimate this thing can themselves have some error. Now moving ahead, we will have